the data that was obtained from the ECG2 file, the coding was typed with CLC because CLC can clear all the text from the command window, resulting in the clear screen. Then the data was transferred in MATLAB by using command load here. Once the data are saved in the workspace, we can use this data to plot the input signal continuous time domain ST by using command which is the plot ECG. After that, the same data was used to plot the discrete time signal which is SN by using the command stem ECG2. Based on here, the data have been converted from time domain signal to the frequency response. The using of FFT ECG2 is required to compute the discrete Fourier transform DFT of the ECG2. The signal was plotted using plot ABS Fourier command and it returned the complex magnitude. From the figure, we can see that there are two unwanted signals appear at 501 Hz and 1.501 kHz. As what we can see, these unwanted signals were not able to be detected inside time domain representation.
Assalamualaikum and salam sejahtera. My name is Hafiz Syazani and I will be presenting on our filter design. We designed our filter as an FIR low pass filter using the MATLAB app called Filter Builder. From here you can see that our frequency specification is set to 450 Hz and 500 Hz. Moving on, I will be explaining on the frequency response. You can see here that the passband frequency starts from 0 Hz to 450 Hz, and the passband frequency starts from 500 Hz up to 1000 Hz. And other than that is the transition band, which is roughly about 50 Hz, and there is also a passband ripple of about 1 dB. Other than that is our filter frequency response in ratio, which is similar to the response in dB. That is all from me. Thank you.
Next, we can use the same command, which is output equal to filter HLP ECG2 and also filter builder, to obtain the phase response, pole zero plot and impulse response of the filter. Here is the frequency response plot of the filter in terms of phase. From this plot, we can see that the phase range is approximately between -33 to 0 in radian. We can see that the phase shift in the passband region is more stable compared to the stopband region. Next, for a FIR filter, the order is referred to the number of zeros of the transfer function Hz, which is a finite polynomial. From this plot, we can conclude that the filter order is 42 since there are 42 zeros in the pole zero plot. The pole zero plot can also determine the stability and performance of the filtering system. We can also obtain the filter impulse response in time domain Hn using filter builder. The impulse response of the filter is actually obtained and derived from Fourier transform. Using the formula for inverse Fourier transform, the impulse response of a low-pass filter turns out to be a sinc function, which is similar with the plot that we obtain here.
Next, we will continue with the output signal. This is the output frequency domain plot signal. From this graph, we can see that the filter that we designed have successfully removed the noise. Then we continue with the output continuous time domain plot. The output signal have become clearer, and from this figure we can see that there is no interference in this output signal. So we can conclude that all the noise signal is successfully filtered by the low pass filter. That's all from us. Thank you.